what is the challenge that we're trying to achieve in the North Sea? If we're going to hit the 2050 carbon targets, we will need to accelerate the build of offshore wind. It's becoming less acceptable to build onshore, so it seems easier to build offshore. I think Wind Europe suggests that 450 gigawatts of offshore wind will be needed. 380 gigawatts of that will be in Northern Europe, which is the Northern Seas and the Baltics and around the colored countries here. Within promotion, we focus on the Northern Seas, and there we figure in our high scenario around 200 gigawatts. I believe my colleagues presented in the North Sea Wind Power Hub presented 180, and in our low scenario we have somewhere around 90. But it seems to be trending towards the higher end of our prognosis. In the deployment plan, we took basically a number of different paths to reach the deployment plan. We looked at the offshore wind scenarios and where the wind would be generated. We've looked at topologies. We've looked at the technological choices that have to be made. We've also looked at, we've done a kind of cost-benefit analysis of if you steer the topology in different directions, what is the best way to actually build a grid? And that has all been on the kind of technical side. On the non-technical side, Work Package 7, which was the subject of last week's session, worked on the economic analysis, sort of cost-benefit, cost allocation techniques, financing aspects, legal and regulatory, governmental and market structures, and these all feed into how you make a decision on how to build a grid. The other conclusion that we had quite early on was that the next step actually has to facilitate the future. And in that we came to the conclusion that for the technology to be ready in time to build a grid, we need to look at projects that are being planned today. There's about a 10-year lead time on building projects. So if we don't look at plans today, we will not be ready to apply the technology in the future. So we looked at some short-term projects, and I'll list those in a minute, but we looked at some short-term projects and looked at how we could adjust those to make them work to test the technology for the future. Promotion, of course, does not exist in isolation. So we've done, what we've also done is we've looked at other programs with which the EU has sponsored, which people have published and so forth. And we've looked at those, and we've made a gap analysis of what other people have done and what we should be doing. We've also looked at the technology that has been developed within promotion and done a gap analysis to identify what is left to do. So the deployment plan is something that brings all these things together and gives a kind of, it gives us, well, we sort of say a roadmap, but it's more a task list of what we recommend people have to do going forwards. I'm just going to zoom in on the topologies quickly, because this is a core of the panel discussion we'll have in a minute. We look at business as usual, where we started. That basically means point-to-point connections. If we look at a national meshed scenario, we're looking at starting to connect but retaining the EEZ borders. If we then look at an EUR scenario, we relax the borders and we let the grid develop in its own way. And lastly, in the hub situation, we're creating larger hubs which concentrate energy and bring energy to shore that way. We of course do it over a time period of between now and 2050, and then we optimize our investment over those periods and the grid development over those periods for each of the different scenario or concepts that we create, and for each wind scenario we've generated. So that way we optimize a structure, and that on that we have sort of made a technical choice, and we've made it a bit like Lego. We're using standard blocks. We're not using new Lego, which has a block for everything, but we're using standard blocks based on the level of technology a little bit, or what's state of the art today. And then we've done performed a cost benefit analysis. This slide gives a quick illustration of what those different topologies look like in 2050, and you can see the different complexity of the structures in each case. Our conclusions actually were quite interesting. I think what we discovered was the lowest discounted capital investment cost was for the island solution. And if we look at the optimization of some of the different factors involved, we could probably improve that further. This though will require higher anticipatory investment, which is an issue. Nobody wants to spend money up front with the risks later and other problems that may arise. We've used the 2 gigawatt N-1 onshore infeed constraint, which results in many point-to-point connections in all the scenarios. A larger cable would have a dramatic cost impact. What we also see is meshing a multi-terminal results in a much lower cable length, but the overall costs end up being similar as protection and ancillary equipment costs are higher, and especially the substructure costs to carry those. Therefore, however, higher benefits are also available from those meshed solutions. What we also found, which was almost counterintuitive, that was the more efficient use of cables within the hub concept and the EUR concept led to higher curtailment. So we had higher utilization of the cables, which you may say is more efficient, but some of the benefits are removed by the fact that you have that higher utilization. So one of our other conclusions was that the offshore topology planning cannot be done in isolation from the onshore grid. So if we look at the 4 concepts, what the 4 concepts allow us to do is we started with the bipole point-to-point, and we went towards a multi-terminal meshed system. And what we discovered is we're allowed, the optimizer created meshed links early, which suggests that they do provide increased benefits, and therefore we could prove that multi-terminal meshing does improve the economic case for the grid. If we look at the next axis, if we went from the 2 gigawatt, what we're calling small hubs, to a much larger hubs or islands, we found that in the long term you have a lower investment and lower OPEX. This is especially if you can relax the onshore constraints, because then you could probably build bigger cables. But we have to be aware that the investment profile is such that you have higher anticipatory investments in hub islands or hub solutions. And you have this curtailment issue that you need to solve somehow. What we were less able to prove was the European dimension. This was probably due to the fact that we had higher utilization. Because of our focus was on evacuation, we had limited interconnection capacity, and that resulted in that curtailment. Also, what we found is our model brought electricity to the nearest point onshore, which was not always the best landing point for the energy, and then you had to transport it to somewhere else, and then you could gain this curtailment. So this is European aspect was not proven in our analysis. I said we looked at some pilot projects as the next step towards a multi-vendor environment. We believe that at the moment we have a fairly standard sort of structure. We believe we have to move forwards, and I'll move through these quite quickly because Case will be able to talk more about our project later. We need to test in an increasing level of complexity the different advances in technology and the different needs of more complex grids. We've identified at the bottom of this slide different real projects taking place or being planned or taking place today where we believe you could apply the technology developed within promotion. We've done some preliminary feasibility studies on these structures. So far, nobody has committed to, no TSO has committed to participating in development of this, but the game's not over yet, and they all realize that the equipment does need to be tested, and there are certain projects that are planned to take this step further. So if we look at the map, you will see that there are about 5 or 6 concrete projects identified. We worked with the owners of 3 of those projects quite closely: the Southwest Link Hansa Power Bridge project, the Wind Connector project, and the Bornholm Island project. And on each of those projects, we were able to do certain pre-feasibility studies depending on the specific needs of the owners of those projects, and we actually have developed our results based on those. As a conclusion of what's come out of promotion, we believe that we are technology ready for multi-terminal HVDC grid development. There are some issues still to be solved, but we don't believe that those are insurmountable. There is further standardization work needed on multi-vendor HVDC grid integration, on functional compatibility, on procurement and contractual compatibility, and on multi-vendor interoperability. What we believe is probably more important and potentially more difficult to achieve is that we'd require international collaboration and coordination to be able to gain the regulatory and legal compatibility, to get project and planning to where it's needed, and to get topological compatibility, the best way to roll out, or the most cost-effective way to roll out a grid. And that all requires political agreement, which is less easy to achieve than probably the technical solutions. And as I just said, the next stage for demonstrating the technology would be a full-scale pilot project, which should demonstrate feasibility and realize those benefits. So that's a very brief introduction. There will be more discussed later on all of these subjects, so please stay tuned. And now I'd like to go introduce Case, who's our project leader. He's the technical coordinator of the Horizon Promotion Project. He has been leader of Work Package 5, which is the full power test facility, and for testing HVDC circuit breakers. He specializes in HVDC cables, offshore power grids, all that we need to build our grid. And I think he'll probably go ahead from there. Sorry. Can we, let me go to, I'm going to make Case presenter. Yeah?
Case, you're presenter now, you can go ahead.
John.
So, is my screen visible properly?
Yeah.
So, great. Yeah. Good morning. Thank you for the introduction, John, and yeah, welcome to everybody in this call. It's my pleasure to give you a sketch, the vision for what we call stepwise organic development of offshore grids. It's quite a high-level discussion, but we are curious about your thoughts and feedback, which you can share with us through the chat box. And hopefully it provides a background for the two presentations that come after this as well. So what drives and shapes offshore grid development? As you probably know, by 2050, some 200 gigawatts of offshore wind generation will be realized in the North Seas. This is a tenfold increase from what is installed today. It may even be more, given that Ursula von der Leyen in her speech yesterday indicated the need to go to even higher renewable energy share and more quickly. In addition, the EU member states must have realized 15% of interconnection capacity to their neighboring states compared to the total installed generation in their countries. Many researchers and planners have asked themselves the question, how should the offshore grid be designed to realize the export of this amount of wind generation and to interconnect the North Sea states? Now, to answer this question, we must go back to fundamental power system planning objectives, which are that the grid must be, of course, guaranteeing sufficient security of supply. It must minimize the environmental impact whilst doing so and minimize the cost of energy. Our main principle in reducing the cost of energy is to introduce competition into what is naturally a monopolistic market. For example, by unbundling generation from transmission, competition is introduced in the generation of electrical energy. And this allows for example, the competitive tenders for offshore wind farms. In some countries, further unbundling between transmission infrastructure ownership and system operation has led to a degree of competition in the development and ownership of transmission infrastructure, and hence competitive tenders for transmission link building. Our main tenet of competitive markets is the absence of significant or unequal barriers to entry. And in transmission grids, this translates to the principle of non-discriminatory grid access, which means that any grid user has the same right to use the grid under the same technical and regulatory conditions and against the same connection cost. This is achieved by imposing a set of formal, technology-neutral, binding grid connection requirements, which are typically known as grid codes. And also by implementing a level regulatory playing field through a long-term, stable, and predictable regulatory framework covering both market design, ensuring a regulated income, allocating liabilities in a clear way, and ensuring clear and stable remuneration schemes for the participants. In the AC national onshore grid, these principles have, over time, led to the development of a highly meshed and standardized transmission grid, with standardized voltage levels, clear connection requirements, which serve all the different users of this grid in an equal but also very reliable way. Several studies have indicated that when we go offshore, such an interconnected, naturally evolving, open access, meshed grid also brings the highest socio-economic benefit to the European consumer. This is, however, not what is evolving offshore today. Now, due to the distances and the power capacities involved, HVDC technology must be used offshore. The map you see in front of you shows all the HVDC systems that are currently in operation or in development in the North Sea today. It also shows the locations of offshore wind farms in different phases of planning, consenting, and realization. The HVDC links that you see are all point-to-point links. They have different voltage levels, as you can see indicated by the different colors that have been used. And these links also all have different converting configurations. Moreover, these links all serve different, distinct purposes, i.e. either the interconnection of offshore wind or the interconnection of countries, and those two purposes are not shared by the same infrastructure. This point-to-point HVDC system building paradigm exists due to many political, legal, regulatory, and system planning reasons. From a technical perspective, the technology to build multi-terminal HVDC grids was considered immature up to now, and due to a lack of standardization and technical connection requirements, the equipment from different vendors is not interoperable with one another. Moreover, different HVDC systems were located far away from one another, so their ratings were typically optimized for their particular business case and not chosen to be compatible with any potential future neighboring links. From a regulatory perspective, the national regulatory frameworks in the countries bordering the North Sea, although adequate for the onshore AC grids, had relatively large differences between them, creating an unequal playing field offshore. Moreover, well-intended supranational regulation designed to overcome this, an example is the 70% rule, did not foresee the need to combine the different purposes into the same infrastructure, forming another hurdle in the uptake of the combined use or so-called hybrid infrastructure. Today, it is possible to see that there are so many HVDC links arising that the terminals of planned and existing HVDC links are geographically close or even in the same location. And promotion research, as John has alluded to, has shown that a significant benefit can be realized if these links would be connected on the DC side rather than on the AC side as they are done now, and thereby form the first baby steps in the evolution of an offshore HVDC grid. Similarly, you can see that many of the planned and existing HVDC links run close to planned offshore wind farm sites and could benefit of being cost-effectively connected to that HVDC link. So how can the current point-to-point HVDC grid building paradigm be changed to enable the future extension into a gradually evolving multi-terminal and multi-purpose HVDC system, which spans several countries and adapts to market needs as they change over time, so that we can connect offshore wind farms in a cost-effective way to shore. We can interconnect those wind farms with one another and potentially even connect them to already existing infrastructure. And this requires a change in the way how we plan, design, specify, realize, operate, and own and regulate HVDC systems. We have to make it technically and physically possible to expand HVDC systems and operate them in a multi-terminal network topology. We have to stimulate competition and avoid vendor locking by creating the technical and contractual conditions to connect equipment from different vendors without a loss of performance. We have to optimize the grid utilization by creating the legal and regulatory framework that enables the connection of more than 2 countries, as well as offshore wind generation for the same interconnected grid. And finally, we need to create clear rules of engagement to enable a transparent and fair governance framework, which introduces competition that respects the sovereignty of the different North Sea states. It's clear that a certain amount of national coordination can have a socio-economic benefit for the national consumer. This relates, for example, to the effective use of marine space and transmission infrastructure, as in the case of offshore wind clustering, for example, the Belgian meshed offshore grid, which you will hear more about later. But it can also relate to the transmission system planning, as is the case with the adoption of standardized platform designs by, for example, TenneT. In China, it's even shown that under a centralized a priori long-term grid planning approach, the realization of a multi-vendor meshed HVDC grid is technically possible onshore. It's however unlikely that such an approach is politically feasible in the North Sea with its many national borders. Conversely, an entirely open access, competitive, market-driven, stepwise grid evolution paradigm may be preferable from a European perspective, but it may be hard to sell this on a national level, as it may not optimize the local national benefits and hence not get the necessary political support. It's therefore necessary to look for a careful balance in which the benefits due to coordinated grid planning on a national level can still be realized and garner public support for the energy transition, whilst not losing out on the benefits of open access European HVDC grid evolution. Now, there are, of course, many roads to Rome when it comes to achieving the target of 200 gigawatts of offshore wind. And the route taken is something that should be determined by energy policy and market needs. but it's important that the route is navigable and familiar in all the North Sea states. And when it comes to highways, in Europe, we've already managed to do this by agreeing on a common set of road design standards, signage and numbering systems, allowing the user to drive from the tip of Portugal into Central Asia without having to adapt to a different driving environment. That leaving space for different national control over the state's control over the actual routes and implementation of where the highway should go. So can we apply a model like this to European offshore grid building? In my opinion, this should be the way to go about it. And the first step in doing so is to find out what is the minimum set of regulatory agreements, functional requirements, technical parameters, and project aspects that we need to agree on in Europe, that we need to coordinate, that we need to harmonize or standardize in order to enable the compatibility and interoperability of different HVDC systems and HVDC equipment to allow this stepwise organic development of multi-purpose, cross-border, multi-owner, multi-vendor, multi-terminal HVDC grids. And in determining what is the minimum set of regulatory or the minimum set of aspects, we should really take into account three aspects. One is that it needs to respect the national sovereignties of the different member states. Otherwise, it will never get the political support that is necessary to do so. Further, we should avoid costly future capex investments. So we should focus on the aspects that need to be harmonized and aligned that might otherwise lead to very costly changes. And lastly, we should not change anything that will threaten the future investor revenue streams. So whenever we determine this set of agreements, we should keep this in mind. An electrical perspective can be given, of course. If you have two HVDC systems, there are three main types of compatibility that need to be agreed on. The first one is, of course, the electrical ratings. These are the voltage levels, most commonly, but also who is responsible for earthing the system, for example. The second one is the syntactic or the semantic compatibility. Can different systems in the HVDC grid actually talk to each other and understand what they are saying? This is a precondition necessary to control and protect the grid properly. And then lastly, there's functional compatibility. Do the different systems in the grid behave in a compatible way? Now, all of those aspects need to be compatible with one another in order to be able to successfully connect different systems. But changing electrical ratings can be significantly more expensive and require much longer term to plan than, for example, changing functional control settings, which could be, in some cases, as simple as a software update. So therefore, the option for least regret should be to agree really on the electrical ratings now. The functional aspects can wait for later. Now, these are just the aspects of technical compatibility that we need to agree on. There's also the alignment of actual projects. This comes to grid planning. There is the regulatory compatibility. We need to ensure that the rules of engagement in the different countries are compatible with one another. And it all starts, of course, with political agreement. And lastly, but certainly not least, there needs to be contractual compatibility so that the way in which HVDC systems are procured doesn't exclude the future expansion into a multi-terminal system. In promotion, we have developed distinct recommendations for each of those levels. It can be summarized as follows. When it comes to political agreement, we need to adopt a common vision of how we want to use the North Sea energy resources and how we want to share this between the different member states in the North Sea, but also countries that are no longer or are not in the EU. Secondly, when it comes to regulatory compatibility, we need to align on multinational power system rules of engagement. This is, for example, the way that we set up a market design, the way that we plan the offshore HVDC grids, and the way that we operate. So system operational guidelines, for example, which currently do not exist for HVDC systems, need to be developed. We need to coordinate the power system planning regionally and across the different users. So offshore wind farm planning, HVDC transmission system planning for interconnection, but also consumers offshore or offshore reinforcements of the onshore AC grid should all be combined within the same planning tool to look at when does it make sense to have an offshore multi-terminal grid extension realization of a transmission need, or if a dedicated link is necessary. Fourthly, we need to agree on compatible electrical ratings for HVDC equipment. Especially choosing a common voltage rating will be very important in order to make sure that in the future we can actually connect two different HVDC systems that we're developing separately from one another in different locations. We need to, of course, also agree on common functional requirements for HVDC equipment. What should the converters do? What kind of support should they give the AC systems? And how should they react, for example, to DC grid faults? This needs to be aligned in order to make sure that we create a technology-neutral playing field to work in. In order to achieve vendor interoperability, we need to adopt compatible interfaces between the different vendors' HVDC equipment. Most notably, this relates to how does this equipment communicate? Can they understand each other? How do they exchange the information? And lastly, we need to align the procurement or best practices for HVDC equipment with this new HVDC paradigm, so that if we can buy a single converter station to, for example, expand an already existing link, and therefore we need to learn how to specify on the DC side how the system should behave and what information is necessary to do so, but also to clearly allocate the liabilities, for example, in these kind of cases. Now, we can formalize these different levels of agreement in different tools. There are the following types of instruments, ranging from multilateral treaties, such as the Paris Agreement on a very high level, all the way through things like the 10-year network development plan, to grid codes, standards, and recommendations, recommended practices. And we are all playing a role in this, from national governments through to standardization bodies. Everybody in this call probably has a role to play in here and is a stakeholder. So my main message is to see what can be the common ground between all of us that we can agree on in order to make the first steps towards achieving this compatibility. So to conclude, incompatibility between different HVDC systems and different HVDC environments in both technical but also the regulatory and legal sense of the word will lead to a suboptimal European power system expansion, as we may see today. And changing this will require a paradigm change in the way that we develop HVDC systems. It's important that we start urgently making steps in finding common ground between all the different stakeholders, both nationally but also vertically, and to coordinate and standardize on political, regulatory, technical, and business levels. And the important aspect here is that we keep on being aware of what will be the benefit in doing this, and to communicate this not only to the people in our own group, but very much to everybody else, the European consumer. How many jobs will this create? What a reduction in environmental impact will this lead to? Because if we fail to do so, then the politicians who will actually need to support this will not get behind us. So we need to always keep the benefit in the back of our mind. International harmonization of project and system compatibility parameters is needed urgently, because if we don't do this, we will end up in a situation where we have a Gordian entanglement of many different HVDC systems that cannot be connected together into one grid to realize that benefit. So in order to achieve this, we should really initiate development of formal technical and operational rules of engagement. For example, multi-vendor system integration best practices, HVDC system operational guidelines, and of course an HVDC system grid code. So with that, I'd like to finish my presentation. Thank you for your attention, and I hand on over to, I believe it's Gert. Is that right?
Yeah, I think Gert will now take over. I believe we need to put him as the presenter. Jochen?
And we're good to go.
Hello, yeah, Kat, are you there?
Yeah, good morning to all of you. Can you hear me and see my screen? Hello?
We
Yes,
do.
your screen is visible, yeah.
Okay, and you can hear me as well. Okay, perfect. Good morning, and thanks for having me on this breakout session on meshed offshore grid. So I'm Gert van Kouwenberg. I work for Elia, the transmission system operator in Belgium, and we're part of the Elia group, together with 50Hertz, one of the TSOs in Germany, and also with Nemo Link and Elia Group International. I'm very happy to have this opportunity to show what we as Elia Group have been doing in terms of development of offshore grid, and also we've been contributing to meshed offshore grid, and how we're also planning to support that future evolution. So one of the first realizations that we did as a group was Ostwind 1 in the Baltic Sea, where we connected two wind farms, two offshore wind farms, Wikinger and Arkona, with 220 kV cables with 3 different cables. What was special there as well, that was that we also foresaw a cable between the 2 different platforms of those 2 different wind farms, creating a 220 kV mesh grid to be able to transport all of that energy out with 3 sets of cables that are being shared. So that was a first step into an AC meshed grid. And we took that concept a bit further in Belgium, where we've developed the modular offshore grid, or the MOG as we call it, where we've developed what we call a plug at sea, an offshore platform that collects the wind energy being produced by 4 different wind farms. And so those 4 different wind farms connect into our OSI, our offshore switchyard, from where we then have 3 different AC cables on 220 kV towards the coast. And so by collecting all of that energy offshore into that hub, we are able to have a cable less. So instead of having to have 4 cables for 4 wind farms, we can do it with 3 cables, taking out environmental impact, and also increasing the redundancy for all of those wind farms. So there we also have an offshore meshed grid in Belgium, and that came into service in 2019. What are we working on today? One of the projects ongoing as we speak in the Baltic as well is what we call the trigger-slack combined grid solution, and was mentioned earlier, a hybrid project. So this is a hybrid project. It's a project that serves 2 purposes. It's on the one hand side, it's the connection of offshore wind farms in Denmark and in Germany, and on the other hand, by making smart use of the assets that are in place, it also realizes an interconnector between those both countries. And as I said, serving then those 2 purposes, bringing the offshore generated energy to shore, but also being able to support further exchanges between countries. As however that part of Denmark and Germany are in different synchronous areas, it wasn't as easy as just putting a cable from the one wind farm to the other. Was also the need to foresee a back-to-back HVDC converter to be able to solve that issue of having those 2 different synchronous zones. So that was an additional technical challenge here in this project, needs to be overcome. And the trigger-slack combined grid solution is planning to go into service in the coming months, and then we'll have in Europe the first hybrid interconnector in service. We're also still working on an extension of, also in the Baltic, of what we had in around the Austrian area called Ostwind 2, where additional wind farms will be connected also on 220 kV, further expanding the grid in that area, or the offshore grid in that area. And that's planned to go into service in a phased approach between 2022 and 2024. That's what we're working on right now. What are we looking at for the future? One of the things that we're planning to do is develop an extension of our modular offshore grid in Belgium. So currently a plan has been developed for an additional 2 gigawatts of offshore wind in Belgium, which we will also connect via an AC 220 kV grid. And that MOG2, as we call it, Modular Offshore Grid 2, will comprise of different platforms, up to possibly 3 platforms, where we'll transform that energy to 220 kilovolts and will transport back to shore via AC cables. And all of these platforms that we will develop will be interconnected as well. So again, that will be a meshed grid, and it might even be possibly connected with our modular offshore grid 1, creating an offshore grid almost over the entire Belgium coast. Again, the goal to improve reliability and redundancy in that grid in a cost-effective way. And then last but not least, we're also investigating to construct a second interconnector between Belgium and the UK together with National Grid Ventures. But we're not looking to develop that project as a point-to-point interconnector, but we're also hoping to be able to develop that project as a hybrid project connecting offshore wind in the UK. So here, as it is an interconnector between the UK and the continent, it will have to be HVDC for certain. So we're looking at it as a multi-terminal HVDC link with one terminal offshore to connect offshore wind farms in the UK. And that could potentially be commissioned by 2028. And as it could be then a hybrid solution, it would allow to integrate the assets that would otherwise be needed for the interconnector and the offshore wind farms all into one asset, leading to reduced environmental impact, reduced local space needs, and also a reduced cost with that solution. So that's hopefully something we can develop, or that we're aiming to develop for the future in order to further support development of offshore wind in the North Sea. Voilà, that brings me to the end of my presentation, and thanks for your attention, and I pass on to Alexander, I guess.
Yep, thank you, Gerd. The next presenter is Alexander Helmedach from Amprion. Alexander is the head of primary equipment at the offshore department of the German TSO Amprion, and his focus lies on the technical aspects of the current offshore projects, and as well as future interconnected offshore systems. So he came from the E.ON Energy Research Center and RWTH at Aachen, which is of course one of our partners in promotion. So he probably knows a lot of the people who have been involved in this project as well. Alexander, please go ahead.
That is true. Thanks for the introductory words. I do know some people, yes. Can you hear me properly and see my screen? That would be my first question.
Yeah, we can hear and see you. All good.
Perfect. Thanks. Then first of all, I would like to welcome everybody. And I would like to use the next few minutes to give you an insight to an initiative that we call European Offshore Busbar. That should be an initiative for future-proof European offshore infrastructure. So an example of a demonstrator as we have been talking and seeing before. The main idea behind Eurobah is to start an initiative on an entire European level of stakeholders to support a path to integrate such large shares of offshore wind as we have seen before, which are planned, and to always look at a system level or have a system level view and to do an overall optimization. We have seen this before, the motivation, but I would like to focus again. So if we look at the European climate goals for 2050 and we are looking at the CO2 neutrality, we see that this leads to a path to the necessity to increase the offshore wind significantly. So we were talking about 450 gigawatts on a European level. If we look at the North Sea, we have around 200 gigawatts of wind power, including this shall guarantee that we can limit the 1.5 degree target, sorry. And then on the other side, if we look at the average time, the duration time to plan such offshore wind park connections, if we are looking at HVDC, we see this is more than 10 years. Then if we have the big aim at 2050 and we do have the planning time of 10 years, it's clear that we have a necessity to have sustainable concepts as of today, and we need to think, and this was said before, today on how we can realize such projects. One idea we had is to create, I was saying before, a European offshore busbar. You can see such a type of busbar on the picture here. And the main benefits of the concept that we do think is we have an optimized utilization of the wind capacities, and this is for two reasons that I would like to show you when looking at the map. So first of all, we do have a mismatch between the offshore potential estimation in the different countries and the load estimation, now looking at the example of 2040. So we do see that we have the two cases where we have way more generation than load and vice versa. So if we combine the different countries, we obviously have the chance to have energy transfer. And second is that when we span such a large busbar, we also have effects, anti-correlation effects, that we combine geographical locations where on one side we have wind and on the other side we don't have, so we increase the stability. What we're thinking is that a step-by-step development with an open approach is the best idea to go into that direction, also because we would like to focus on the entire system, to optimize the entire system. And this means looking at the offshore grid, but also looking at the onshore grid. And we did find out in some simulations that if you optimize both at once, you can reach different optimization results. But moreover, it's clear if we want to reach the EU target for 2050, we can not only look at the electricity sector, but we need to look at all energy domains. And this means obviously including sector coupling, so to an optimization of the entire energy sectors and looking, for example, at power to hydrogen. So I would like to zoom in now into the different steps of such a planning, where step one would be the offshore integration based on the national planning processes that we have as of today, with the approach to move from single offshore platforms to cross-linked system. You see the transmission links here in yellow, and the dots are then the platforms that shall be prepared to be connected at a later stage. So that should feature something like a European offshore plug. And then in step two, to connect those platforms internationally to small clusters. So to start within the single EEZs, to cluster up and test the system, and then in step three to continue to have the international offshore busbar, so to continue with the modular approach and to do the full realization of the system then with the benefits that I listed before. The future offshore integration requires sustainable concepts as of today. We have pointed this out before. It's clear that the national and European climate goals rely on offshore wind extension if we want to reach the climate targets. So obviously, the importance of reliable infeed does increase a lot from those resources. And we do have an increase of the need for energy transits. I have shown this on the map before. It's clear that then we need to move from the business as usual towards an offshore interconnection to create increased flexibility and to have the one system view. The point we are at now is that we are about to enter the next generation of offshore connection systems. They are just around the corner. So we're looking in the Netherlands first at the 2 gigawatt, 525 kV DC systems, which are to be realized then a few years later also in Germany. And we are planning to standardize the system as much as possible, so to have similar platforms. And when we are entering now this next generation, we do have an enormous benefit if we think today of how such platforms could be layouted or designed so they allow for connection later on. The open European approach is needed because the larger the system is, the more benefits and synergies are taken. And this is why, and we think to realize this in a modular stepwise development, such as also proposed in promotion, basing on the existing planning processes. I pointed out before that we would need offshore grid ready platforms so we can plug and play step by step. And most important is that we have the standardization of the interfaces, so we are able to connect the platforms with then the goal to reduce cost and to only work on a need-based extension. The close international cooperation should be used to discuss different approaches and to discuss the solutions transparently, because we think there are issues that need to be discussed and where we don't have the full answer as of today. So we need to work step by step and see what the best solution is in the end. Some technical aspects we need to focus then is when we look at topology, what are the best grids? Is an AC connection or a DC connection best, or hybrid interconnections? We have seen an example for an AC connection just in the presentation before, but we also see projects, we've seen this at the beginning of this seminar, examples of multi-terminal DC connections. Theoretically, we could also have hybrid connections, so partially AC, partially DC coupled. If we include DC with a certain number of terminals, we obviously need DC circuit breakers, so we have to look at the design of those circuit breakers as it has been discussed a lot in this context, and then we need to look at fault detection and fault handling. Regarding the operational aspects, obviously not only normal operation is of interest, but also looking at the different fault strategies, independence of how the grid is set up. So this brings pros and cons for the different hybrid or AC or DC structures. We need to look at possible reconfiguration after fault. So we can have, for example, a clustered operation before fault or afterwards, depending on what the best strategy is. I would like now to sum up what the main idea of the initiative is. So we try to move from concepts that we have today to an implementation, to move towards a demonstrator that is set up in the area of the existing planning processes. So to take next generation platforms and look how we can integrate here possible connection options. The first pillar is, as I have said, the modular extension. So the system composition should be extended step by step. So we are in line with the existing planning processes. This leads to the second pillar, a robust progress, where we're not at risk to lose the offshore goals because we have fallback options, meaning that if the interconnection does not work out 100%, we have the point-to-point connections that we know how to connect and how to build, and we can improve step by step through the process. third pillar is we would like to have the one system view, as I told before, so to combine a system-oriented optimization and also an interface standardization, looking at the different energy domains, looking at on and offshore grid, and to have most important an open approach. So to all sit at one table, discuss the ideas, bring the partners together, and talk about the necessary standards and create ideas that we can have an autonomous implementation of the pieces of the puzzle in the different countries. That brings me to the end of my presentation. I would like to thank you for your attention, and I'm more than welcome to feedback questions, and I'm looking forward to the discussion round. Thank you.
Thank you, Alexander. We actually have got a whole list of questions that have come rushing in. And so I'll introduce you, Hannah, who's going to pose the questions. We're going to have to move quite quickly, I think, because time is flying. So Hannah, can you come in with the first question, please?
Yes, of course. Good morning, Alexander. Good morning, Gert. So first question for Alex is, how do you see market-driven evolution of the grid versus optimization, which feels more like central planning? So the question of, yeah, is it market-driven or is it kind of an optimized solution, which requires more central planning? I think you're still on mute.
Sorry, I think I had a little technical problem. I try to repeat the question. So central planning versus modular planning, is that correct? Did I get the question right?
Yeah, central planning versus
Okay.
a kind of more natural market-driven evolution.
Okay, yeah, well, we do think that the complexity of the integration of offshore wind at such a large scale is so high that we need to go step by step, and that we need to look on a step-by-step basis on how the interconnections could work. So we have in Europe, I think this is different to, we were talking about China before, such a complex framework of regulatory boundary conditions that we need to see how this evolves during the coming days. So we have to focus one on the technical challenges, but second also on how regulatory aspects can be changed to be realized to interconnect offshore wind farms. And this is why we thought it might be clever to have in a first step an international connection, so where we are able to test the standards first and then move for an entire busbar system. Because if we look today, we have so many open challenges for the regulatory aspects and market aspects, it probably would not be possible to realize the entire busbar of today. And there are a lot of discussions that need to be made. So we need to see how the market discussions, how the regulatory discussions evolve, and then how we can combine this with the planning and the discussions of interconnections. And this is why I try to point out that first of all, we need to talk with everybody which is involved, and second of all, we need to have a feedback loop. So if we make a proposition as of today with the boundary conditions we have of today, that might be obsolete by tomorrow if boundary conditions change. So we need to have an approach where we are not all in today, but we do small steps and then fine tune later. That's the main idea. I hope this answers the question.
Can I come in to get Gert there, because Gert, the ADS solution at the moment is largely AC and is not particularly in line. Are you going to participate in a Eurobar type solution?
Are you going to make me sign something?
No, you don't have to sign. It might be the more difficult one to connect.
Yeah. Well, I think we can all agree that cooperation is key. Yeah. There is no single one party who can do the entire challenge as before is on their own. So we'll clearly need to work together between TSOs, but not only TSOs. It's governments, regulators, offshore wind farms, probably forgetting a whole bunch of other important stakeholders. But so cooperation will be key. I think we're already cooperating in a good way in for example, NSOE, where you have the TUI and EP looking at grid development. But there might be additional things needed. There might be around offshore more strengthened cooperations needed. And so that's something that we're certainly open for. And if you move down another step further, looking into concrete projects, then you always have to see, does that project, that scope that's being defined now, does that make sense for my system? Do I have something to contribute? Can I make, is it worth the money that I'm part of that evolution? And that's an ongoing exercise that you always have to look, you have to do that all of the time, and that can evolve. And so when there is an interesting infrastructure opportunity and interesting project, we'll certainly be part of that.
Okay, Hannah, next one.
Great. Another question actually for Gert from the audience. So this is quite a project-specific question. So asking whether the 220 kV link between Arkona and Vikinga, apologies for my pronunciation, was it foreseen when the platforms were built? If so, how was the anticipatory investment justified? And if not, how hard was it to make the necessary adjustments afterwards? And a similar question on that, for how hard was it to extend the Baltic infrastructure with the Kriegers Flak link?
Yeah. Good question. I'm unfortunately not knowing the details of those projects. So these are the German ones, and I wasn't involved on those in that time. But you said anticipatory investments, and that's something that also came up in our modular offshore grid project in our MOC. It's always, I think, every TSO will face that discussion. How do you level off that risk, bringing certain investments forward, where you're maybe not sure that all of those wind farms will come, what the size will be, and so on. And I think there, good engagement with regulators, with authorities is important, that you can clearly set out what is the minimum, the base scope, and what are smart ways to make your solution better that will cost a bit more, but that will in the long term be worth their money. I think that will be the balance that we'll have to find in the decades to come, always trying to balance that out. What is useful to do a bit more spending up front to create potential without having to have too many euros at risk, and finding the smart ways to have an additional investment. And one concrete example we have there on the modular offshore grid as well is that we have some additional spare base where we can add in more cables that we can now also use to create a connection to the modular offshore grid too, which didn't cost that much, but it creates opportunities.
Great, thank you. Coming back to Alexander, we've got another question from the audience. This is asking around, do you have good data around how often you have kind of good wind conditions in one part of the North Sea and not in another? And therefore, would the main driver for the Eurobar concept be transmission or evacuation of that wind energy, or also transmission of onshore PV or hydropower to other sort of places of demand?
Well, the idea started to really looking just at offshore wind and how it's possible to integrate this. And the question or the motivation came out from the planning processes, where we saw that with a high increase of the aim coming from Germany, that changes a lot in the path. And then we thought it doesn't just make sense to optimize on a part of the puzzle if we want to solve want to reach on European level the climate goals. And then we thought what structures were possible, motivated by the project, like promotion or other projects, other thoughts. And we did do some simulations, and we saw that the anti-correlation effects between the wind patterns, so if we take wind data, is significantly rising when we move one country further. So if we connect just wind farms next to each other, the correlation is quite high, obviously. And the further we move, and we have that possibility, if you just look at the North Sea, and we could also combine other seas, but just at the North Sea, we do have this effect, and this was results of preliminary simulation. So obviously we want to continue. So we're just at the start, but the effect is, there's an indication that this effect plays a significant role, yes.
Great, thank you. And then a question I think that perhaps both to both of you, so maybe come to Alexander first. What is the most important aspect that needs to be coordinated now to enable future compatibility? And how could this coordination be achieved amongst TSOs or other key stakeholders?
Well, we believe to throw the idea into the round to get everybody on one table. And this, you pointed out exactly the stakeholders, so the TSOs, but also the manufacturers, and to get the regulatory stakeholders into the place to be able to address technical questions on one side, but also regulatory aspects. And regarding technical questions, one big issue is the standardization. So are we able to interconnect different platforms from different vendors? What is necessary to be solved in the future? And then when, or if we want to, let's say, put a connection in 2035 or something, what is necessary to be prepared now so the platforms are able to talk to each other on the electricity level? And we have seen all the details of this aspect before on the electricity level, but also on the communication, on the control aspect. And we do think that everybody benefits. So we can only reach those high targets if everybody works together. And this leads to an increase of the projects, and everybody benefits, even the manufacturers, because we are only able to have such a large scale of projects if we increase the efficiency. And this can be done through standardization, not only in the single type of platform, work on standardizations. That's what we see in the different countries. We've seen this as an example in Belgium, in the Netherlands. So we have standardizations in the platforms, also in Germany now with the new generation of platforms, and the manufacturers benefit if they participate. That's our thought.
Thank you. Yeah, I think highlighting those win-win situations, I think, is going to be key.
Hopefully, yes.
And do you want to add anything on that point around what's the key kind of or most important aspect that needs to be coordinated now to enable kind of future compatibility, and what's the role for key stakeholders in that?
I think Kees mentioned it in this presentation. I think their voltage is key. Having the same voltage on your HVDC link is a, let's say, tremendous important element to be able to link them in together. But it remains that they really set to go and standardize on voltage, because you're still trying to, let's say, develop a project today. And even if you know that maybe you have a 5 to 5 kilovolt level, which will be standard in the years to come, that might even bring an additional cost to projects that you're developing today. So then you get back to that balance of, is it worth foreseeing that optioneering, that possibility? Is that already worth it today? Or are there still cases where you should just optimize your own project and maybe not look at the whole potential? So that's, I think, an exercise that needs to be made in every project, taking in account that it's very important voltage.
Okay, thank you.
What do you see as the time frame that you have to think about? Because I think what we noticed in our analysis is that we have to keep looking further and further ahead. So if you're looking, if you're saying you have to balance, what is the balance? There's anticipatory investment, but the payback time may be much later.
So there is no clear answer on what the time frame is. I think that is also, I mean, again, then we can take it to more the national view and how your regulators see that and for who those benefits are. So I don't think there is a clear-cut answer there. let's say it's trying to do, let's say, the bit of tailor-made, even while you're trying to standardize a large block, you will also always have a bit of tailor-made on top of it.
Okay. Hannah.
Just picking up one, again, very project-specific question for Behet. Has a HVDC link from the offshore wind farm directly to Brussels or Antwerp also been considered in grid planning?
So if we're talking about the modular offshore grid too, there we've looked at a range of options, because I've only spoken about the offshore part, but it also requires important reinforcement in the onshore grid. I think it was already mentioned earlier. Those things go hand in hand: offshore development and onshore development. And so when looking really at the start of a project, a lot of different options were investigated. But we quickly saw that we had different drivers. It wasn't only about connecting offshore wind, which is a very important driver, but it was also about making our grid in that coastal area more robust. It was creating additional connection capacity for the Nautilus project as well. And there we saw that the best solution for that range of drivers, and there were other drivers as well, was to do onshore AC reinforcement. And by doing so, we could also do an offshore AC extension and keep that distance to be covered to a limited, let's say, limit distance. But it isn't excluded that if further connections need to be made on top of what we're looking now at for 2030, that we need to go much deeper into the grid with HVDC connections. That might certainly be something that's on the table for the future.
Thank you. I think that covers all the kind of audience questions. Thank you very much for answering those so thoroughly, both of you. I'll just hand back to John for any further questions.
No, I'd like to. I think we'll just call it a day there. I'd like to thank you both for spending your time with us and your vision today. It's been very nice. It's a bit of a strange video experience, but sort of I'm sure we can. The thanks are there, and your presence has been valued immensely. Thank you very much. And if you can make me presenter again, please, I'll move on to the next section of the presentation. Thanks again, and let's go on.
Well, thanks to you as well for having us.
That's okay.
Thanks for the chance and for the attention.
Yeah. Okay. Okay. Let's go back to what the deployment plan was. We went into wind generation, as I said. We have been into the cost benefit analysis. We've been into various topologies. If I look at today, we have a number of people available who are going to answer your questions. The ones in green are not available. That's Wim van der Veen, who did our work on cost benefit analysis theory. So the work package has 6 public deliverables. We're going to focus on deliverables 12.2 and 12.5 today, and 12.4, which are the optimal scenario development, the final deployment plan, and 12.5 is a supplement on the short-term projects. All these deliverables are on the promotion website if you want to read them, or if you want background information. If you want a guide to get, some of them are quite large, so if you want a guide to get through them, contact me or one of the other people who are available today, and I'm sure they can steer you towards the information you require. The first speaker is Felix Rudolph from FGH. Felix it's probably not the right order. Felix is going to talk about the benefits analysis done, and he's on vacation, so we'll let him talk first. I will advance this on behalf of Felix. So if he could put on his webcam, then we can start his part of the show.
Yeah, hello. Good morning, everyone. Can you hear me?
Sounds all good.
I can hear you. Yeah.
Yeah, okay, great. So, good morning. Yeah, as John already introduced me, I'm Felix Rudolph from FGH in Aachen, Germany. I studied business administration and electrical engineering here at RWTH Aachen University and work as a research assistant at FGH since 2017. And my role within promotion was researcher in work package 2. And yeah, the task leader for the benefit analysis of the CBA for work package 12. And the benefit analysis, the next slide, please. So the idea of the benefit analysis was that we need a comparison and an evaluation of the concepts, of the offshore concepts we developed. And for that, the best way to evaluate these concepts is an operational dispatch simulation, which we developed at FGH. And for that, we used steady state modeling. So we modeled the European transmission system only as a node model to make it a bit easier. And because the offshore topologies were the most important things to model in the simulations, these were modeled, of course, in more detail. In order to model everything for up to the year 2050, we used market data mostly taken from the 10-year Network Development Plan, TYNDP 2018, which was the most up-to-date doing when we started the benefit analysis. And we slightly modified this market data and extra interpolated it. The operational simulation occurs for 1 year. So we simulate 8,760 hours for 1 year per concept. And for the year 2025 to 2050 in 5-year steps. And of course, we did that for each concept and for each scenario. So for the high, central, and low scenario as well. And in the end, after we simulate 1 operational year, we can evaluate the benefits by calculating key performance indicators, KPIs, from the results. And the benefit key performance indicators we evaluate in the simulation are, for once, the socioeconomic welfare, the renewable system integration, the CO2 variation, so the CO2 emissions, and the security of supply adequacy, which would be the loss of load expectation in the future. Next slide, please. The conclusions we derived from the simulations are, for the benefit analysis, that heavy meshing, so for example, in the national concept we developed within the project, that has the most advantages in the quantitative benefits. But the disadvantage is that it also has the highest associated costs in construction and operation, for example. The operational simulations have also shown that an increasing share of renewables in the system leads to several time periods of energy supply and demand mismatch. So in order to avoid that behavior, we would need some kind of storage to shift everything together. Another result is that the benefits of offshore system expansion is not only quantifiable in the North Sea countries, but we have also seen that the benefits are shown in, I would say, the second row after these North Sea countries. So not just in Germany, we can see benefits in Poland, for example, Czech Republic or Austria as well. So when we simulate in the future, or when we have similar simulations in the future, it's always a benefit to simulate these countries as well. Also seen was that an increase of transfer capacity on the interconnections, especially onshore, should be considered in a joint European offshore development. So when all the North Sea countries develop jointly, the onshore interconnections should be included as well in the process, especially as it is possible that some countries or some markets are getting or becoming an exporter of energy. And this is not yet considered in the TYNDP 2018. And therefore the NTCs available in the TYNDP are a bit different. Of course, in the TYNDP 2020, new scenarios were developed and this could be different. Also, as I already said, could you please go back to the slide? Yes. The development of flexibility options has to start in an early expansion phase of the offshore system to avoid curtailment and high redispatch costs. As I said, we have this energy supply and demand mismatch. And in order to avoid that, we have the option of demand side management, DSM, power to X, so hydrogen production, for example, or just classic storage facilities, for example, battery storage, which could be used to avoid this mismatch. But these flexibility options weren't simulated in this benefit analysis. So for further research, this could be an option to include them as well. Yeah, that are my main conclusions and the introduction of the benefit analysis. If there are any questions from the audience, I'm happy to answer them.
There are no questions so far, so go right ahead, please.
I have a quick question. One of the things that we didn't do is actually convert everything into or monetize every factor. Is there a way we can relate and weight these factors in comparison to be able to sort of manage our steering of the steering of construction or steering of ideas?
Of course, all the different benefits we determined, we didn't give each benefit an monetary value in the end, because, for example, the CBE methodology of the TYNDP doesn't suggest that doing so. And for giving different weighting factors to these KPIs, I think from my point of view, that's more subjective matter, and best way to go forward would be to develop weighting factors within the NSOE, for example. So we should, for example, giving a weighting factor for CO2 emissions or curtailment and so on should be developed jointly with all the countries or markets included. But we didn't do that within the project, and I think that's a whole different topic.
Okay. If there are no other questions, Hannah, are there any other questions? Then we'll move on. Yeah. Thank you very much, Felix.
Thank you very much.
Enjoy your vacation, and
thank you.
And we'll see you again soon. Yeah. Okay. Yeah. Thank you. Okay. For the next section, we're going to go over to Olivier, I believe, is going to be doing the talking. Tractable were responsible for our wind scenarios and the topology planning. So let me allow Olivier to take over the speech, at least. You there?
Okay, thank you, John. Do you hear me well?
I hear you well. Fine. Yeah.
Okay. Okay, thank you, John, for giving me the floor. So I will present you a few slides that summarized the video we presented on the that is available on the offshore, I would say, development of optimum scenario. It's a work that has been done by Tractable, but in cooperation with all the partners of Work Package 12. And here I will present what has been, I would say, led by Pierre Reynaud, my colleague, and myself. If you go to the next slide, John. So the main goal of what we try to achieve was to somehow provide a scenario of what would an offshore grid could look like, and what would be the possible evolution from 2020 to 2050. And as we know, we have quite a lot of uncertainties in terms of regulatory, legal, and technical barrier. We know, for example, that the technology for meshed HVDC offshore grid is not yet mature, but in promotion, we show that we made a big step forward in this aspect. All the technical work package gave us somehow a green light on and quite good confidence that technology will be there and will be available to build an offshore grid. So what we tried to do was to somehow explore a set of scenarios, but we couldn't indeed explore all the possible scenarios. So we specifically consider 2 dimensions. The first dimension is what we call the concept, and we explore 4 concepts. So the BAU is, I would say, only point-to-point HVDC connection. Then we had the national distributed concept, where we allow connection between offshore wind farm, but we had a national constraint, meaning that the installed wind capacity in one country had to be evacuated to the same country. In the European distributed concept, this constraint is removed. So we could have offshore wind farm of one country directly connected to another country. And in the 4th concept, it was a different concept. It's allowing I would say the creation and the building of artificial island in the North Sea, where you could connect wind and also potentially storage, and then evacuate the wind to shore. The second dimension that we consider was the wind scenario, and in promotion we developed 3 wind scenarios ranging from 100 gigawatts in the low wind scenario up to 205 gigawatts in the North Sea. Yeah, you can go to the next slide, John. Just to give you an indicative timing of the temporal evolution, this is a picture. It doesn't mean it will be the reality, but what we could observe is in the first phase, and if we look at the existing project before 2030, most probably we will have, and we say, optimized point-to-point connection. Then starting around 2030, we will have a multi-terminal HVDC grid. And therefore, we have to be sure that all the technical, legal, and regulatory barriers are alleviated at that time to allow for multi-terminal connection. And indeed, we could imagine to have also the expansion of point-to-point connection to interconnector, and then the development of those hybrid assets. By 2040, what we saw, I would say it's not exactly what has been presented by Amprion in the Eurobar concept, but we saw in the high wind scenario a kind of backbone in the Dogger Bank, because you have somehow a short distance between the offshore wind farm. And there you indeed have this backbone to exchange energy from one country to the other via the offshore grid. And then the grid continue to evolve after 2040, and you have higher multi-terminal structure that could potentially be connected at the end of the time horizon. On the main conclusion, John, on the next slide, I would say we learned a lot through this process, but I would like to stick to 2 main messages here. The first one is that the planning of an offshore HVDC grid is really challenging. We have many uncertainties to consider. In terms of numerical complexity, it's very difficult. to manage all those complexity, because here we only consider the offshore grid planning, but in reality you should consider the offshore but also the onshore grid planning, and that you should be able to optimize everything. And we would say that it could be needed to have an adaptation of the grid planning guidelines, and potentially also the tools to be able to do this coordinated onshore and offshore grid planning. If you include in the equation storage, sector coupling, and so on, it becomes even more complex. And also the second message, and that was already discussed today, is really the need for a high level of coordination and cooperation between member states. And that for the development of offshore wind farm and the offshore grid, for the development of the offshore grid and the onshore grid, but also in the maritime spatial planning. So indeed, the determining the best location for the wind farm. And that has to be done not only at the national level, but also at the European level. And there we will see a real benefit to have this meshed HVDC grid. And therefore, we would recommend that a coordinated maritime spatial planning, but considering the grid planning constraint, would facilitate the development of offshore wind and HVDC offshore grid. Those were my 3 main slides for that one I wanted to present today. So maybe we can stop for question. Those were backup slides, so I don't really need to go through those.
Let's go back. Okay, so thank you very much, Olivier. If I look at the European and the national scenarios, they look quite similar, and yet they came with very different conclusions. Can you give a little bit of insight into why they're so different?
Yeah, so the main difference between the national and European concept is indeed that in the national concept, we only allow wind generation of one country to be evacuated to another countries, and then we somehow optimize the interconnection to other countries. While for the European concept, we allow the connection of offshore wind farm in any possible country. I would say the limitation of the European concept that we studied here is that we didn't optimize the wind scenario at a European level. We optimized the wind scenario using a national target. And if we imagine that we optimize the wind scenario at a European level, and then we use the European concept, we will see even more differences and potentially a bigger benefit for this European approach. So I would say that even if in your question you say it's different, in reality it should have been more different and more beneficial for the European concept.
Okay, thank you. And how stable are the wind generation scenarios? I mean, you've linked them to national requirements. What we now see, well, actually during the project, what we've seen, I know that we've seen, is that that the political situation has changed in a number of the countries, and the ambition has similarly changed. Are they still? Are these ambitions going to change more, or do you think that reality might catch up on us?
Yeah, if I can remind a bit the history on the development of those wind scenario, I think it took us within promotion more than 1 year, maybe 1.5 years to come with those numbers. So initially we looked at the energy outlook and at many reports, and our low wind scenario was quite high compared to the literature at that time. But now if we compare to other publication, the high wind scenario seems the most realistic when you compare to national and European ambitions. What we have done in those wind scenarios was to do a screening of the areas in the North Sea, and exclude areas not that couldn't be used for wind, because you have a lot of exclusion zone for other application or other I would say for other use than wind, and we basically specify some areas and assume a power density of, let's say, 8 or 9 megawatts per kilometer square, and then came with a total value of wind potential. So in terms of that's how it has been done, and we had many discussions. And in those numbers, we fixed them, and then we applied the four concept. What we realize now is that we should have done, or what that should be done, is to optimize at the same time the wind location and the choice of the concept. But that's a very difficult exercise.
Yeah. Okay. Thank you very much, Hannah. Are there any questions on Teams?
Yes, we have one question come through from the audience. So just reading this out, it says, in your key messages, you don't mention sector coupling. With the increased mismatch between generation and load, how would you value this compared to onshore grid development?
Can you repeat the question?
Yeah, of course. So it says, in your key messages, you don't mention sector coupling. So coupling between kind of electricity and gas, for example. With the increased mismatch between generation and load, how would you value this compared to onshore grid development? Saying that could be maybe power to gas offshore as opposed to doing onshore grid reinforcement.
Yes. So yeah, unfortunately, we couldn't consider all dimension, and that's why we say that it would be interesting to have adapted grid planning guidelines and tools to handle more numerical complexity. Yes, here we limit our study to the development of the offshore topologies, and at the interface with the onshore grid, we specify some onshore hosting capacity per landing point. And indeed, we didn't investigate sector coupling or large-scale storage, but indeed that could be part of the equation and remove or reduce the need of some transmission assets. But we cannot provide a quantitative value on that.
I think it's worth mentioning that that was out of scope for promotion from sort of day one. And it is something that has become increasingly important as the project has developed. And certainly when we look at Felix's work as well, we do see that somehow we will need to consider sector coupling either onshore or offshore if we're going to make this work. I think how it works or how you optimize that was out of scope of our work. Yeah.
Just got one further question at the moment. So the question is, how sensitive are your designs to the various national regulatory limitations, such as the largest allowable single component contingency?
Yeah, that's indeed a good question. It's something we try to analyze. It's difficult to quantify, but what we assume as input assumption is that the cable size is lower than the maximum loss of power in feed. So here we have cable size of 2 gigawatt in our study, and we assume for continental Europe that the maximum loss of power in feed is 3 gigawatt. So then indeed you don't push for the need for a parallel path. In the future, what could happen is that you could have bigger cables, but most likely that might need a higher voltage level. But you could imagine for environmental reasons to have cables very close to each other, and then that the risk of losing two parallel cables is there. There is a risk. And if you want to protect and to secure the grid for that, you would need a parallel path. And in that case, what we call the national and European concept would be even more meshed and interconnected. But then those concepts will really be more beneficial than the other. So we did some sensitivity, and for all sensitivity, the coordinated approach was more robust to any change that we try to do in the sensitivity analysis.
Okay.
Have we got time for one more?
Yeah, I think so.
One more question. I think this is actually quite a quick question from the audience. It just says, is electrification of oil and gas platforms in the North Sea within the scope of work for the promotion project?
Yeah, so we had many discussions about electrification and yeah, oil and gas platform. We don't, I would say, explicitly include it in the design, but indeed it's an option to connect oil and gas platform to the offshore grid. That could be an important source of reliability of supply for those platforms. So it was not explicitly used in our calculation, but I don't see any I would say any limitation to include oil and gas platform in this offshore grid.
Thanks, Olivier.
Okay.
Thank
I think
you.
that was all those questions
Okay.
for the moment. Thank you. Back to you, John.
Okay. I'd like to go on now to the next section, which is and introduce Yongtao Yang. Yongtao is from DNVGL, and then he's been doing work on how we cost individual elements of the grid. So Yongtao, can you come online? Hello, is Yongtao there?
Once.
Yeah, okay, I hear you now. Hello? Or not? Are we missing Yongtao?
Can you hear me again? Sorry.
Oh yeah, I can hear you now, yeah.
Yep. Okay, yeah, my name is Yongtao Yang. I'm working at DNVGL. As John said, in promotion, I'm working in work package 2 and 4, supporting the DC grid modeling and protection system designs. And then I'm working also in work package 12. In this work package, leading the task force to collect the data.
Yongtao, you have an echo.
Okay, wait a second. Let me see what. Yeah, it's here. So.
Hello? Now you've gone all together.
Is it better now?
Yeah, that's
John?
better. Yeah, go
Okay.
for it.
Yep, sorry. Yeah, I'm working in work package 2 and 4, supporting the grid modeling, and in work package 12, I'm leading the task force to collect the cost data for offshore power transmission system. That's well, and then in work package 16, we're working on the control hardware in the loop and the power hardware in the loop testing for wind turbine generator and MMC VSC converters. And here in this in this context, I'm talking about the work we are doing in work package 12, collecting the data. Not only collecting the data for the existing technology, but also collecting data for emerging technology and for their future development from today until 2050. So there we have a small team, but also works almost all the consortium partners within promotions. So the summary of the activity within this context is that, as I spoke a bit earlier, that collect the cost data for existing component, existing technology, and also emerging technology as inputs to the cost benefit analysis. So that's we are talking about like converter stations, cables, platforms as the building blocks, unit cost of those. And then for existing for component of existing technologies that we are mainly based on the literature review, the in-house database, and yeah. But for emerging components, we will be use two methods to get the cost. One is what we call the inferential models. So that's the method. This is the method used to collect to establish the cost for those component which you have a similar products in use. For instance, that's what we use to estimate the cost of a full bridge VSC MMC converter station, which is until today has rather limited to the project reference in operation. So we have to utilize a similar product, which is half bridge VSC converter station, which has been deployed quite widely in Europe, but also in the world around. So you will have a good cost model for that, so that we can find out the difference between them and then make an estimate. Another one is the bottom-up approach, which is basically the rather unique products. We don't find any good reference or something similar you could refer to. So that's basically we establish the cost model by looking at the configurations and to summarize the total material cost and then establish the cost model for such a product. And in addition, we also established a framework to assess the future cost development of all the components, all the technology we mentioned above, from today until 2050, which is aligned with the promotion as envisaged meshed offshore grid build-out time horizon. So the key step is that first we break each individual component into different cost elements, which is the manufacture cost, the transportation installation cost, the PM cost, and then also the land use or right of way cost, and then the R&D cost, and then the etc. Also the risk premium and the profit margin. And then for each of those cost component, we also divide them into the cost drivers that include like labor cost, engineer cost, also the raw material that include the metals and raw oils, and also the energy cost of those components. And then we consider the megatrends of each cost driver, like the automation, the robotization would probably most likely drive down the cost of laborers and engineers hours. And also we also predict the metal cost, metal and raw material cost development based on the World Bank prediction on those ingredients. By that we can summarize and make a projection on how each individual category of component their cost will development until 2050. And then we also make a comparison of our prediction with the so-called learning curve effect. Basically, that's or you also called as Wright's law, which means that for each doubling of accumulated installed capacity, the unit cost would decrease by a certain percentage. It was found out our prediction agrees quite well with the learning curve of 10 to 15% deduction, with the 10 to 15 deduction of unit cost per doubled installed capacity. Yeah, that's wrap up my my summary.
Okay, thank you very much, Yongtao. Yeah, how realistic do you think your costs are? Because I know that you had to rely on various sources of people, and there's a lot of secrecy. The different manufacturers were not allowed to read your report and this sort of thing. Do you think your results are reasonably, because that, I mean, it drives our cost-benefit analysis, which is relative,
Yes.
but yeah.
Yep, indeed, a good question. I mean, we have also a debate with ourselves. How do we substantiate such a cost estimate? So we have two at least for the existing components, at least what we can do is benchmark against the whatever we can find on the public available information, like the tender contract value or announcement, to trying to to establish and also at least to calibrate the cost model. So that's the one part. For the especially for the future development, that's really difficult because we don't have a time machine. So the only thing we can do is one thing, of course, is compare with the so-called rights law. But also, I would also point out this is still a framework. There's a lot of assumption we have to make. It will be like a discussion. This is a framework enable us to discuss with the stakeholder to get their opinion. For instance, how automation or energy efficiency will impact the cost of different components. So that's it's a mixed answer.
Yeah, I mean, if my worry is if we actually build 200 or 450 gigawatts in Europe and similar amounts are built in the US and China, that we won't disturb the commodity prices and things like this materially, and the costs may go up, or we may not achieve the savings that have been predicted in your work. But I think I must admit I was impressed by the work done. If people want to know more, they can about the methodology. They are welcome to go to the presentation made by Yongtao, which is quite interesting. The report is available to consortium partners, but is restricted towards manufacturers and certain parties that may have competition issues. Thank you very much, Yongtao.
Thank you.
Thank you for spending your time. Is there any other questions, Hannah?
No further questions at the moment. Thanks, John.
Okay. Let's move on then.
Thank you.
The next speaker is Jelle van Uden. Jelle has been focusing on the cost-benefit analysis and the integration of conclusions into the deployment plan. He's an advisor he's an advisor at Tenet. So, Jelle, would you like to go further? Hello?
Yeah, just trying to push all the right buttons.
Okay.
Here I am. There you go. Yeah, please go ahead. So part of my work within promotion was to do the costing part of the cost-benefit analysis. And I've spoken about this in my presentation that was online this week. So I'm going to quickly go through what we did there. So part of the costing method entails translating the topologies made by Tractable into components, and we have to basically combine the cost of components that Yongtao made for us in this research with the topologies, and by doing so estimate the cost of the different grids. And underlying the methodology for costing the offshore grid is the decision tree for components in the topologies, and this is shown here. So first, for each connection to shore, the model that we use checks whether or not the offshore wind farm is at a certain distance from its offshore converter. If this distance is under 25 kilometers, we assume that the 66 kV AC inter-array cables from the offshore wind farm can be directly connected to the AC/DC converter. If this distance is anywhere between 25 and 50 kilometers from the offshore wind farm to the offshore converter, we assume that there will be a need for 150 kV AC cables to cover this distance, and therefore you would need a 150 kV transformer and a dedicated platform for that. And similarly, if it's anywhere between 50 and 100 kilometers, we assume there will be a need for 220 kV AC cables and therefore a transformer and platform. Then the AC/DC converter for each of the offshore wind farms can either be placed on a platform in all of the topologies or on an island in the hub concept. So that's the second choice that we have to make there. And then thirdly, from that offshore platform and converter, we can go to shore, where we will have a DC to AC converter onshore in order to convert the DC power back to AC and feed it in the onshore grid. Or alternatively, the cable going from the AC/DC converter can go to another AC/DC converter, either on a platform in the national and European concepts, or on an island in the hub concept. And this is the underlying methodology for translating the topologies into separate components. And once we have those the separate components, we can combine this with the information from Young Tao's methodology and essentially calculate the entire cost of the offshore grid. Next slide, please, John. So yeah, to summarize those costs, we can see that the hub concept, the third row here, has significantly lower cost than the business as usual. And this can mostly be attributed to the fact that a large amount of offshore platforms, very expensive support structures, will be replaced by artificial islands in this concept. And therefore, you can see a significant decrease in cost in this concept. The national and European concepts it's quite a remarkable outcome in our analysis, is that the costs are actually higher than in the business as usual, and this is mostly due to the fact that you would need protection on this within these particular concepts. So whenever a fault may propagate such that the loss of power is higher than the reference incident that the offshore wind farm is connected to, you see that you need protection on those specific parts of the grid. And where in the business as usual, like Olivier explained, the topology is designed such that you will never have an incident that can lead to load shedding on shore. The national and European concept, of course, because of the meshed nature of a lot of grid components that may, if a fault occurs, lead to load shedding on shore. Therefore, they need protection, and that protection is quite expensive. So we see a decrease in cable length in these concepts, but not a decrease in total capex. The OPEX follows a quite similar structure. That's because it's relative to the capex, because it's a certain percentage. So that was my quick my quick recap of my presentation that you could see this week.
Okay, thank you very much, Jelle.
No problem.
Hello. Hannah, are there any questions online?
So just a couple of Q&A. So one quick question: is there an optimal size for islands?
That's a good one. There must be an optimal size for islands. yeah, we try to have a little bit of a look whether or not there's an optimal size for an island. But what we found is that it's really dependent on the location of the island compared to where the offshore wind farm is in relation to the onshore grid. So you can imagine if an offshore wind farm is located between an island and the onshore grid, there's actually not so much of a saving for that offshore wind farm to be connected to the island, because you have a large reroute of the cable. We did see in the low wind scenario that there's not much of a saving anymore. So in the high wind scenario here, you can see a lot of savings in the capex, and as the capacity of the islands decline throughout the scenarios, you see that this large saving also declines. Even so far that in the low wind scenario, there's not much of a distinction anymore between the business as usual and the hub concept. So yes, definitely there will be an optimum, or at least a size in which you would say you go for an island rather than platforms. But we did not manage to really dive into those figures and find that out.
Great, thanks, Jelle. I think you've actually answered my second question already, so so great answer. Yeah, no more questions from me. Thanks, John.
Okay, I think we better move on because time is short. Maxine, can you come online, please? Thank you very much, by the way, Jelle.
Can you hear and see me now?
I can hear you, and I can not see you, but probably everyone else can.
It should come out. Okay, then I'll just go ahead. Well, good afternoon, I should say, everyone. Welcome to this part of presentation where I will quickly make a recap of the work that we have done on short-term projects. As mentioned by previous speakers, similarly, you can find a full presentation available on the promotion project website. So today I will just focus at a very high level on the work that had been done in this subtask of work package 12. A couple words about myself. I'm currently working at DNVGL as an energy markets consultant, and within promotion, I was responsible for the short-term projects coordination. Interestingly, I have been in promotion quite some time ago as a member of another company working from TNT. So I've been looking at the project from different sides, and I think that helps to have a better picture of the work specifically in work package 12. We can move to the next slide, please. We have initially identified 6 projects that allow some of the typical elements of meshed offshore grid to be deployed already in the short term. Eventually, we have done pre-feasibility work on 3 of them, which you see in the bold font. So those are Southwest Link and Hansa Power Bridge connection, wind connector cable, and Bornholm Energy Hub, also known as Clean Stream Project. Moreover, we have had some dissemination workshops and supported North Sea Wind Power Hub with some of their questions. What makes this task special, the short-term project task, is that, if not mistaken, more than 10 promotion partners combined their effort. And this allowed us to explore the projects from very different dimensions and to capitalize on the expertise of industry subject matter experts with very different backgrounds. So what you can see on the right-hand side, that we have developed technical concepts to integrate HVDC. So these are very much looking at the dimension of components, how they should be connected, what are the control strategies, protection strategies, and so on. We have conducted feasibility studies on those initial concepts to select those that can actually be implemented. As a next step, we carried preliminary high-level cost-benefit analysis to understand whether those proposed concepts can actually bring societal benefits and not just serve as a platform for testing, And interestingly, some of those projects do bring societal benefits. Furthermore, we made a review of market, regulatory, and legal barriers where those were present. And finally, as a result, we came up with recommendations for the potential project implementation if it was to be done in the future. Next slide, please. So during the past 5 years, Promotion project brought technology to the lab testing level, and this is well known. We tested HVDC JS, we tested HVDC circuit breakers, control systems, and so on. However, it's a joint conclusion within the consortia that identifying short-term projects such as Bornholm Island, Wind Connector, Southwest Link, and Hansa Power Bridge, it's a cost-effective way to deliver pilot environment within real projects already in the short term, and in this way make first steps towards the deployment of a full-scale offshore grid. Therefore, we have performed preliminary studies to support these real projects, and as a conclusion, we see that technology is ready, but there are still outstanding risks related to procurement, interoperability of HVDC technology, multi-vendor contract management, and so on. So the projects that we have identified, they actually try to minimize these risks, although there are still issues to solve. So as a final note that I would like to make is that there needs to be a motivation to go further, and as we heard recently during the DENETWEB conference, for example, where representatives from Denmark, Germany, and Netherlands were present, everyone actually starts to talk about going in the real world, developing pilot projects, implementing something, and this is seen as the best way to actually start the process. And that's our main message. We believe that it's time to go out and build something. Thank you. That was it from myself.
Thank you, Maxime. Hannah, have we got questions for Maxime?
Just a couple of high-level questions. So could you just provide a little bit of background on why these particular projects were selected and the criteria for selecting the projects?
Yes, sure. Thank you for the question. So why these particular projects were selected and what's the criteria for selection? The way the projects have been selected is often where we saw that some more traditional HVDC connections have potential to be somehow amended in a way that would make them look more as a part of meshed HVDC grid. So as an example, I think the best example is Southwest Link and Hansa Power Bridge. Those are two interconnectors that have one of their ends at the same substation. So these are HVDC links, which we thought they could be integrated on the DC side, which is a good way to provide some additional availability benefits and operational benefits and so on. And at the same time, this is a very typical element of the meshed offshore grid as it is presented in the deployment plan. So to sum up, I think the criteria is whether there's a way to modify the projects in such a way that they resemble one of the building blocks of meshed offshore grid. And those building blocks, I believe John has shown them a little bit earlier today, the slide where you have seen several grid topologies with growing complexity from left to right. So that's kind of what we were looking for in the real world.
Yeah, to add to that, I think it was a little bit opportunistic. We had some creative ideas from members of the consortium to create the proposals, and we had partners that were willing to offer their projects for our analysis. So it was a kind of, there was an opportunistic side to the effort as well. And I would like to thank those partners that participated or provided those opportunities as well. Anything else, Hannah?
No, conscious of time, so I think I'll hand back to you, John.
Okay. Then the next speaker is Serge Pouzin. Thank you very much, Maxime. Serge is from the Supergrid Institute, and Supergrid Institute had the rather delicious task of working out how we could protect somewhat more complex grids than now exist, and how we can protect the DC, which is slightly different to that, and how much it's going to cost, because that's another major issue. Serge, are you online? Silence. Hello?
Yes.
Oh yeah. Okay. Good.
John,
Thank you.
John.
Yeah. Welcome.
So, thank you, John. So, good morning, everyone. So, I'm Serge Poulin from Supergrid Institute, and my role in the project. So, I was the leader of a dedicated task regarding cost-benefit analysis for protection point of view. And this in this task, we developed some methodologies and tools to try to assess the performance and the costs of different protection system. And we use this methodology in the context of Work Package 12 in order to assess how far the different protection strategy which have been studied in Work Package 4 and Work Package 9 mainly could be extended to large-scale DC grid. So, John, if you could move to next slide, please. So, as I said, our main contribution in this context is that we develop a methodology and we define, in the context of Work Package 4, key performance indicators able to characterize a methodology from both performance and economics consideration. There are many different protection strategies. They have different performances and also different costs. And this tool was expected to bring some decision support tool regarding which could be the right strategy with the right performance regarding AC/DC system requirements at the right cost. So we also participate to the development of a cost model for DC circuit breaker with Work Package 12. Yang Tao already spoke about that, and also with the contribution of Work Package 6 through University of Aberdeen. And then we apply the methodology to large-scale DC grid to try to give some inputs and support to Work Package 12. So we consider several fault carrying strategies, and we compute the different KPIs regarding it. And then from that, we try to define some main takeaways to be a support for decision making, as I said. So John, you can maybe go to the next slide, please. So there are a lot of outcomes. So I try to summarize, but it's a bit long, but I try to go quite fast regarding our analysis. So the first one is a large set of protection strategies are technically applicable to large-scale DC grid with mainly cables. The study has been done with mesh grid with cables. And regarding DC grid security and reliability perspective, the size of the DC grid is not a limitation factor, whatever the strategies, protection strategy. So impact on AC system stabilities is a key driver for the design and the selection of the protection system. This AC system requirements are more related to AC system characteristic and to level of power exchanged with AC system through the DC grid, but to the side of the grid itself. As such, it is expected that both fully selective and non-selective strategy could be applied for the protection of many large-scale DC grid configuration. Particular attention has to be made in case of large-scale DC grid exchanging high power with AC system with high grid impact requirements. That is to say that this AC system could be operate near their stability limits. In that case, using non-selective strategies or considering fully selective strategies, backup protection sequence could bring some stability limits variation. So we can think that fully selective strategies, which are expected to have lower grid impact on AC system, could be preferable, but we need to have a particular attention to the protection sequence impact. Fully selective strategy, non-selective strategy could then have some limited application, but it is really a case-by-case assessment. Implementing partially selective strategy through some grid splitting approach could be a possible solution to reduce the impact on the AC system when using non-selective protection strategies at a quite low additional cost, as it has been shown in one example. Also, a partially selective strategy in grid splitting approach could be also a solution to allow some extensibility of protection system in case of extension of the grid. Regarding cost, no protection system is considered inapplicable due to its excessive cost. We shown that the protection system cost is generally lower than 10% of the full DC grid capex, whatever the size of the grid. However, there are some significant reduction of capex if we use some specific non-selective protection strategy with a converter breaker for clearing approach. Is why we identify that there could be a factor of 2 regarding the cost of the different protection strategy we have studied. This protection strategy using a fast hybrid DC breaker could cost twice the capex of non-selective with converter breaker for clearing strategy. At the end, we can say there is no single preferred protection strategy which outperforms all other protection strategies. And the selection of the right protection system is a question of finding, as I said before, the best techno-economic option. We think that it is a real benefit to have so many different options for protecting the grid that allow to find, as far as possible, the best trade-off between performance and cost. So that's the end of my presentation. So if you have some question, thank you for your attention.
Many thanks, Serge. You just had one question come in. The question is, can HVDC grid protection be added to an existing HVDC system as an afterthought, or does it need to be taken into account in the specification of the main primary equipment, such as cables, when the system is first designed?
Sorry, I didn't really pick up the question.
So, sorry, so the question is, can the HVDC grid protection be added to an existing system as an afterthought, or does it need to be taken into account when you're doing the main specification on design of the system?
So the question is, can we extend, if I understand, the protection strategy at existing HVDC system?
Yeah.
Yes, okay. Yes, I think that we can include existing asset in a new grid, and the protection system can be adapted to the existing system. Maybe we will have to consider the full system, the new full system in a whole, in order to assess the performance, and maybe if in the already existing system there are no DCCBs, maybe we need to implement some firewall between the existing system and the new system in order to comply with requirement coming from the different DC and AC system, because one of the main driver for selecting the protection is what could be the impact on the AC system. So if the existing already existing system do not implement any DC breakers, we need to consider that.
Yeah, can I sort of add a little bit of nuance to this? If we're building a grid, I think the statements from Amprian are very valid, and the statements we've had earlier. The chances are that the grid will be constructed incrementally. So people will build something here, and other people will build something there, and we will connect those together. Is it necessary to anticipate the end state in the design of the DC protection, or will that be an incremental sort of build out? Or can you adjust your strategy as you go, or do you have to think of it from the start?
I think that at least you need to have a quite good idea of what will be the grid in the first steps. We do not really need to have the full picture, but at a certain level, you need to know what would be the different step of the first step of development, mainly to clarify the constraints coming from many AC system grid impact requirements. We need to clarify that, and when we have clarified that, we can select the best protection strategy. Then, of course, if the grid evolve afterward, there are several ways to evolve. It could be evolution of the size. It could be an evolution of the size of offshore system, or also it could be an evolution towards more inland penetration. In that case, you will maybe have some combination of offshore system with cable, mainly with cable, and onshore system, which could involve some overhead lines. In that case, I think that one solution could be to define different protection zone, because if you have overhead line or cables, the behavior of the system is different, and at least I think that we will need some different protection zone with different required performance, and this protection zone could be separated by some firewalls device in order to implement different strategies in a full system. And I think that so doing, you will not put in question the already implemented strategies. I think we can combine different strategies by clearly define different protection zones.
Okay, thank you very much, Serge. I saw another question fly by, Hannah. Is that?
Yes, yeah, one more question's come in. So the question is, currently only one European manufacturer can commercially deliver HVDC circuit breakers. Do you see that as a challenge for the competitive development of HVDC grids?
So it's about the maturity of the development of DC circuit breaker question? Yeah. Yes. So today there is a quite good progress which has been done in promotion project regarding the increase of TRL. So we of such breakers. So we can expect that in the coming years some DC breakers could be commercially available. The limitation maybe today is that we do not really know about the reliability of such breaker in a operating condition in a network. But it's why in the promotion project, one of the main proposal was to experiment in some short-term project how far this DC circuit breaker could what could be the performance in a real life operation of such devices.
Yeah, can I add to that? I think what promotion has done is it's tested 3 different circuit breakers in a lab situation from 3 different manufacturers. Those circuit breakers have all passed their tests as far as I understand so far. Therefore, the next stage for them is to move out of the lab and into an industrial situation. Without that industrial testing, I don't think anybody knows what the long-term performance will be. So I think, and the 2 of those were from large-scale manufacturers, and the 3rd one is from a smaller manufacturer, but all of them have a history in large manufacturing environments. I think we have to move on, Serge. So thank you very much. I know that you also have an extremely interesting presentation available on the promotion website, a number of them actually, because there's also in other work packages. There are some interesting presentations. So I'd like to thank you very much for that. I'd like to thank also Wim and Lawrence. I don't think there's been any questions on the presentations that have been shown, but there's been some, they have both made also interesting contributions to Work Package 12, which are on the promotion website and should be watched by people later. I'd also like to thank Hannah, who's been a massive contributor to this project and to supporting us today, and to Jochen as well. Just a quick recap on the statistics. Work Package 12 included 16 of the 34 partners within the promotion project, and yet our goal was to actually create a consensus amongst them. I think it's been a great cooperation, and I think it's impressive how everybody has tried to work together to reach a goal. I think that those 34 partners multiply when you look at the amount of cooperation that's going to be required to achieve an offshore grid. So I think we have to be aware of the complexity of relationships between people and look at that cooperation carefully. The representatives of the consortium came from 11 countries. We've been working on this for 4.5 years, so there is a huge amount of information. The documents are all for our deployment plan only are around 250 pages each, so plenty of reading, but you can also use them as a reference document to look at areas of focus you want to. The project had a budget of about 42 million euros, mainly going on technical research to get where we are today. So these are our partners, and these were the work packages which were all available. I would like to mention that on Monday we have our live final conference. I'd like to thank everybody for for participating and for listening in. And if you have any further questions, please feel free to contact us. And if you need any backup information or anything like that, please let me know.